Good evening. My name is Atharva Bhalilkar. Today, I will be presenting my project titled Efficient Prompting and Fine-Tuning Strategies for Controlled Concept to Sentence Generation. This project was completed for the MSc in Data Analytics for the module Deep Learning and Generative AI at NCR. Let's start with the background and the motivation, in which we will explore the research question first. The research question that I have explored is fine-tuning with lightweight prompting and LoRa useful in control concept to sentence generation compared to heuristic baselines? The objectives will uh, here are to compare heuristic, zero shot, few shot, and LoRa fine-tuning approaches to evaluate the BLEU, Rogue L, Meteor, birth score, and coverage. And we've applied ChrisDM for structured and reproducibility. We have also analyzed both numerical and qualitative results. Let's move over to the dataset overview and methodology. Dataset used was CommonGen, a benchmark for concept to sentence generation. It contains over 32,000 training examples, over 900 validation, and 1,400 test examples. To fit within the GPU collab limits, uh, I have worked with a subset of 8,000 training samples. The methodology followed was ChrisDM. This has ensured a systematic approach and reproducibility in the project. Let's talk about implementation. Uh, we have implemented this project mainly with Google Colab. The frameworks and libraries majorly used were Hugging Face, datasets, transformers, PEFT for LoRa, and for evaluating metrics. The model setup for this project was FLAN T5. It's a small primary model. Option to switch to FLAN T5 base and LoRa for fine tuning. For reproducibility, all random seeds are fixed and all the code is structured. Let's go over the code walkthrough. Uh, let's look at the code. This notebook is organized for an end-to-end pipeline. So we start with setup, then we import the data, we pre-process it, then we apply four methods. We evaluate, we apply albation, and we generate some samples. We also perform some error analysis and save its results. The goal here is to compare a heuristic baseline, zero shot, few shot, and LoRa fine tuning on a common gen dataset with standard text gen metrics, plus a custom concept coverage metric for constraint satisfaction. Here we start with installing all the dependencies. Then we import all the important packages and libraries needed. Uh, we set something such as seed. We set it to 1337 just for reproducibility and further use. Then we load the common gen directly from Hugging Face. Each row has 3 to 5 concepts and a human target sentence. Because this is a free tier GPU project, I take a fixed seed subset of 8,000 training examples, but I keep the full validation and test set. That gives us a fair eval while staying under runtime limits. Now we move to the prompting, formatting, and concept coverage utility part. Uh, we convert a list like human, surfboard, wave. These are a word of list, which are the concepts, into a natural instruction for T5. Example, use all these concepts in one fluent sentence, that is man, surfboard, and wave. The concept coverage is pretty simple. It's just a simple function that checks a fraction of the required concepts appeared in the generated sentence. So it checks for case sensitive, limitized, and normalized text. This lets us measure the constraint directly alongside the fluency metrics. Now we implement our four approaches, that is heuristic baseline, zero shot prompting, few shot prompting, and LoRa tuning. So for the first one, um, that is LoRa tuning. We wrap T5 model with PEFT, targeting the attention projections. We train it just for one epoch on 8K subset to stay within the time limit. Uh, this will then generate the adapted weights. Here we fine tune all the models and we get some metrics. The outputs are saved in a JSON format under the outputs folder. In the next part, we evaluate all the methods on the same validation set and we save its metrics. Here we mostly standardize all the approaches and the coverage metric. For that, we use an evaluate model helper. It will run the generation on the validation slice. It will compute all the metrics, return a row for the final metric table. Here are the metrics. We can also see the error analysis for LoRa in the validation set. We finally compare the models by plotting a few charts. These are some of the sample outputs. As you can see, it headlines with the concept, and then each approach tries to form a sentence out of that concept. These three are just random examples. Let's move with the evaluation section. So as we can see, the baseline achieved a near perfect concept coverage of 0.97, but very low fluency scores across BLEU, Rogue L, Meteor, and Bird score. Zero shot prompting was the strongest overall. It had the best fluency and semantic similarity, the highest BLEU score of 9.52 and the Bird score of 0.54. Few shot prompting, the performance close to zero shot with slightly better concept coverage, which is 0.88 versus 0.8829. LoRa tuning on the validation set had decent results, but weaker than the prompting models. On test performance, BLU Rogue Meteorel is zero, Bird score is nearly negative, which means it's showing overfitting and poor generalization. The Albion table represents the minimal differences between few shot and zero shot. A few shot gave only a tiny coverage advantage, while zero shot was slightly better on fluency metrics. These are some of the random examples where the sentences were formed based on the concepts. So, in conclusion, the outcome was successful. So we successfully compared heuristic, zero shot, few shot prompting, and LoRa fine tuning concepts to sentence generation and common gen. The performance highlights were showing that zero shot and few shot prompting had the best overall fluency and semantic similarity, while few shot was slightly better in coverage and LoRa tuning is promising in validation, but it failed to generalize on test data, hinting towards overfitting. Uh, Significantly, lightweight prompting can deliver competitive performance. with much lower computational cost, making it practical for resource limited environments. For future work, we propose that we investigate hybrid heuristic plus neural models, extend to larger multilingual datasets, and explore constraint aware decoding or reinforcement learning to better balance the coverage and fluency.